Hello, everybody, and thank you for joining this lunchtime seminar organized by Young Second. Our speakers today are Daniel Pohoryles and Konstantinos Gkatzogias. Both are scientific project officers at the European Commission's Joint Research Center, and they will talk about integrated seismic and energy retrofitting of buildings. Before moving on to the talk, there are a very few housekeeping rules to go over. Please, can all guests keep their videos off and microphones on mute during the seminar. We're going to have a Q&A session after all presentations, but please feel free to type your questions in the chat at any point. Please note that the seminar is being recorded and will be uploaded onto the SECED YouTube channel. So by dialing into the event, you consent that any views or opinions you share are being made public. And first, let me introduce myself. I'm Marco Baiguera. I'm a lecturer in structural engineering at the University of Southampton, and I'm chair of the Young SECED committee. For those of you who don't know what SECED is, SECED is the Society for Earthquake and Civil Engineering Dynamics. Is the main forum in the UK for people coming from both industry and academia who have an interest in earthquake, blast, and other types of dynamic effects. And within SECED, members under the age of 35 are represented by the Young SECED Members Committee. So currently there are 11 committee members who dedicate their time to organize a mix of activities directed to young members, such as site visits, the annual fund, and this lunchtime seminar, for instance. I would like to remind you about two upcoming events organized by SECED. The first one is the Mallet Milner Lecture, which is the most significant event organized by the Society every other year. The 18th lecture will be given by Alain Pecker, a professor at the l'École des Ponts et Chaussées in Paris. We'll give a lecture on the interrelationship between a practice, standardization, and innovation in geotechnical earthquake engineering. The lecture is on the 31st of May at the headquarters of the Institution of Civil Engineers in London. Attendance for the lecture is free, and there are tickets available for the reception, and more information is available on our website. And I would like to highlight that the event is still going ahead despite the rail strike announced for the day. So the tube and some rail services around London won't be affected, hopefully, much by the strike. So I look forward to see some of you in person soon then. And finally, our 2023 conference in September in Cambridge. The title is Earthquake Engineering and Dynamics for a Sustainable Future. So please stay tuned for many other events organized by SECED through our social media channels. And now moving on to the talk, I'm very pleased to have Dr. Daniel Pohoryles. So I'd like to invite you, Daniel, to start sharing your screen while I'm introducing you. So Daniel is a scientific project officer at the European Commission's Joint Research Center, currently working on the development of holistic rating system integrating sustainability, functionality, and aesthetics in line with the new European Bauhaus initiative. His research at the JRC focuses on the combined seismic and energy retrofitting of existing European buildings. And currently, Daniel is the scientific project leader of the PAIN Fluid project that's investigating the use of physics-informed neural networks for estimating the heating and cooling energy demand in buildings. And his research background includes evaluating the seismic behavior and retrofitting of structures with expertise in full-scale experimental testing, as well as numerical modeling. So past experience includes postdoctoral stays at the University of Toronto and at the Universidad Católica de Chile, as well as a postdoc and a PhD in seismic retrofitting at Epicenter University College London. So without further delay, I will hand over to Daniel for his presentation.
Thank you, Marco, for the introduction and for the invitation as well to speak here today. I hope you can all see my shared screen.
I believe at the moment it's for me it's black, but
It's black.
maybe, yeah, I don't know for others. Can see the mouse hovering, but yeah. Okay, now we can see your, yeah.
And now again?
It's black again. We can see the PowerPoint. So maybe there's an issue by sharing the full screen. Okay, perfect.
No, it works perfect.
Yeah.
Yeah, sorry for the short delay. So yeah, as Mark already introduced, with Kostas, we are working on integrated seismic and energy retrofitting of buildings at the European Commission Joint Research Center, specifically in the Safety and Security of Buildings unit. And the presentation that we give to you today is split into two parts. I will start by giving you a bit of an overview of, let's say, what the motivation and background for combined or integrated seismic and energy retrofitting is. I will give you an overview of different technologies for integrated retrofitting that can be found already in the scientific literature, and then some practical experimental examples with participation of the JRC. And then Kostas will take over and speak about a framework for regional prioritization and an impact assessment for building renovation that has been carried out also within the framework of a project at the JRC. So before saying all this, maybe some of you don't know what the Joint Research Center or JRC is. So we are a science for policy institution. We're Directorate General of the European Commission. And the purpose of the JRC is to provide independent and evidence-based knowledge in order to support EU policies and have a positive impact on society. The JRC has its headquarters in Brussels, but has many different or 5 different sites across different EU member states. And we are working at the biggest site, which is the Ispra site in northern Italy. So having said all this, obviously the research that we carry out here always has to have some kind of a policy context. And for the work that we present today, in particular, the EU Green Deal that you probably all have heard about already, forms this framework, let's say the policy framework in which we are working. And in particularly, we're interested in the renovation wave initiative, so supporting this initiative, which aims at increasing renovation rates across the EU, so at least doubling them from the current rate. And also the Energy Performance of Buildings Directive, which is to be enforced and aims at making buildings more energy efficient and also boost renovation rates, while at the same time also in the long-term renovation strategies of the member states, other things such as fire safety or risk related to intense seismic activity should be considered. So we really see this renovation wave, let's say, at the nexus of different policy areas, which range not only from energy efficiency and circular economy, but also disaster risk reduction and safeguarding our built cultural heritage. So at the JRC specifically, there's a few projects that deal with the topic of integrated retrofitting of buildings. A major one was the pilot project on integrated retrofitting, which was a project funded by the European Parliament and looked at integrated retrofitting from a very broad perspective. So from technologies that can be used to methodologies for assessing, but also impact assessment. So most of the work that we present to you today actually stems from this project. And at the end of our presentations, you will also see some recent reports. So we have just at the end of last year published a series of reports on this topic, so that if you're interested in this topic, you might find a lot more information there. Another example of a project at the JRC that I've contributed to is the IRIS Plus project, which deals more with an experimental assessment of specific technologies. I will talk a bit more about this later as well. So this is a project, again, on defining technologies for seismic plus energy retrofitting schemes for existing buildings. And this was carried out at the European Laboratory for Structural Assessment, which is our lab here at the JRC in Ispra. So to come now to the, let's say, the why. Why do we care about this topic, and why is this such an important, why is building renovation such an important topic? So as you will all know, in Europe especially, our cities and buildings have quite an old age and obviously are aging as well. So data from Eurostat suggests that 80% of the EU building stock was actually built over 30 years ago, and more than half is more than 50 years old. So having said that, this means that many of these buildings have been built before modern energy and seismic or structural standards have been put into place. This explains also why 75% of the EU building stock is considered energy inefficient, which in turn leads to really a major share of CO2 emissions and energy consumption in the EU being related to the building sector. So here you can see some figures. 40% of the EU energy consumption is related to buildings. At the same time, and particularly in, let's say, Mediterranean or Southern European regions, the participants of these meetings will be very well aware there's a seismic risk, and over 170 million Europeans are actually exposed to the earthquake hazards. And if this is combined with an aging building stock, with degrading materials, or with buildings not built to current standards, there's obviously a very high risk for devastating consequences, as you can see here with failures of buildings or heavy damage to buildings. So what can we do if we have our building stock that is, let's say, aging and materials are degrading? We could do nothing. We could just take no action, which may seem, let's say, the cheapest option at the beginning. But then when we consider that the buildings are energy inefficient, combined with high energy costs and the cost to our environment due to that, as well as with the risk of earthquakes happening, and if the buildings are structurally deficient, there's a risk of damage or collapse of these buildings. This cannot be an option. Recently, a lot of energy renovations have been carried out across the EU, and this is obviously something very good when we look at the energy efficiency of buildings. But if we're in regions that are earthquake prone, and if we don't assess actually the structural capacity or the seismic resistance of these structures, there's the risk that if an earthquake comes and no intervention has been done on the structure, the building will still collapse, or the damage will still occur. And then we have a building that has now a higher value because there was already an investment into the energy renovation, and the losses then accordingly are even higher. So if we want to improve the structural and energy performance of the building stock, an option would obviously be to demolish the old and insufficiently well-designed building and construct new ones, and construct them according to modern standards. Buildings would be very highly energy efficient, while at the same time ideally also resisting the earthquake loading on the site. This may sound like a good solution, however, we think about the scale of the problem. So the large amount of buildings that actually need retrofitting or renovation, this will not be economically viable. It will not be sustainable from a life cycle perspective, and it will change, let's say, the appearance of our cities so drastically that this can just not be an option. And finally, if you have some cultural heritage buildings, you may not even be able to do this because these buildings are protected. So another solution, the one that we're investigating here, is integrated seismic and energy retrofitting. So by applying the energy retrofitting, the energy efficiency can be improved, and at the same time, for also improving the structural resistance through seismic retrofitting, the building can also withstand the earthquake loads. This allows to make our building stock sustainable, while at the same time also making it more resilient to the risk of natural disasters such as earthquakes. This brings a lot of advantages, of course, reducing economic and human losses from seismic events, but also reducing the impact of reconstruction or repairs that are needed after seismic events, that are also environmental impacts. It reduces labor time for renovations, as the two retrofitting schemes can be applied at the same time. And obviously the energy efficiency part will reduce the need for heating the buildings or for cooling the buildings if done adequately, while at the same time improving the resilience of our building stock through the structural aspect of the retrofitting scheme. And finally, integrating the two together also provides some further cost effectiveness, which might further incentivize people to renovate or retrofit their buildings. So now, after having, let's say, explained what the need is, I will go through some examples from the scientific literature of technologies that have been proposed already for combined or integrated retrofitting technologies. So this topic is actually something that has emerged in the last maybe 5 years, and it's really an emerging topic in the scientific literature, with a lot of publications coming out in the last couple of years, especially. And within the framework of this pilot project that I described before, we've carried out a literature review on combined and integrated retrofitting techniques, where we identified different types of technologies that have been proposed for integrated retrofitting. And we have found that, let's say, the technologies that have been proposed range really a lot in terms of the level of maturity of the technology. Some of the works are just pure concepts and just really proposals, while others have already been validated experimentally or even applied to case study buildings. And when we talk about retrofitting of buildings or renovation of buildings, it's always important to consider that any comparisons that are being made always depend a lot on the building needs. So retrofitting is never a unique solution. There might be many different possible retrofitting solutions for the same buildings, or some retrofitting solutions that are more adequate for certain kind of buildings that have certain kinds of deficiencies or use certain kind of materials, or even it depends a lot on the status of the building. Is this a cultural heritage building that really needs to be preserved and protected, or is it a very simple office building that doesn't have any architectural value and where it's just important to upgrade it to modern energy and seismic standards? Having said that, we have found more or less 4 main avenues that have been proposed for combined and integrated retrofitting. You can find more details about this again on the state-of-the-art review that we recently published, but I will present briefly now some examples of these 4 without being exhaustive. So if you want more details, please refer to the publication. The 4 main, let's say, paths that we found include exoskeleton solutions, envelope interventions, which means basically looking at the existing walls of a building and intervening on them, strengthening them and improving the thermal insulation of these buildings. Another path would be replacing the existing envelope of buildings. And the final one is retrofitting just the roofs and the floors, so the horizontal diaphragms of your building. What we have tried to do is to assess these different solutions, or the solutions that have been proposed, based on a multi-criteria assessment system, where we look not only at the improvements in structural safety and energy efficiency, but also at the sustainability of the materials that are being used, at the costs, more or less, of these interventions, as well as at the disruption time. So how long do people need to leave their houses while this intervention is being carried out, and the level of integration. So is this really a truly integrated retrofitting scheme where seismic improvements and energy improvements happen at the same time, or is this more of a combination of 2 different schemes that can be applied, let's say, one after the other or at the same time? So to start with, integrated exoskeleton solutions are based on, obviously, the application of a structural exoskeleton, which is an external self-supporting system which needs its own foundations that can be connected to an existing building, most likely a vulnerable RC building or a steel building maybe as well, that currently has a low dissipative capacity, and for which the exoskeleton can provide additional strength and stiffness. It's typically not applicable to masonry buildings, however. And some examples of these include, as many of you will know, external bracing, RC shear walls, maybe additional RC frames that can be applied, or bracing shell exoskeletons. And what can be done to make them combined or integrated solutions is to either apply the energy function as a separate one, as you can see maybe also on the image on the left, on top of the exoskeleton, you can apply things like photovoltaic panels, green walls, smart louver systems, or even add additional balconies, add additional floors. So this can really support, let's say, the energy retrofitting solution. Or it can be fully integrated in the sense that if you have a shell exoskeleton, you can also add the thermal insulation or the green wall as part of the shell. I will give you some non-exhaustive examples of proposals for integrated exoskeletons. One that has been applied already to case study buildings in Japan are integrated facades that are really a very simple system where on top of buckling restrained braces, a louver system can be mounted, and like this, let's say, heating of a building can be reduced from the solar heat gains, and like this, the cooling needs are reduced. So this is really a very, let's say, simple system, but is already an early example of integrated exoskeleton solutions. While on the other hand, let's say more advanced solutions would be the two steel-based solutions that you can see on the right. So either steel-braced shear wall exoskeletons as the ones proposed by Bellini, onto which, as you can see, all sorts of shading system, green walls can be mounted, or also diagrid exoskeletons, which form a shell around the building and onto which multiple different things can be mounted, which can provide an architectural upgrade to the building, but can also be considered as an energy upgrade of the building by applying photovoltaics or green walls. The benefits of integrated exoskeleton solutions is that the business downtime can typically be quite low, as also residents don't necessarily need to be relocated. As I shown before, the exoskeleton can actually provide an architectural upgrade to the building, but it can also provide more living space. So it can be the addition of new stories or the addition of terraces or balconies. A very big advantage as well is that such solutions are typically reversible, demountable, and repairable, so they're also easy to maintain. However, it comes also with some, let's say, less desirable aspects, which are that these solutions are highly invasive. They also change the appearance quite a lot of the building, which in some cases can be beneficial, but in other cases, for example, heritage buildings, this might not be suitable. On the other hand, the need for new foundations may mean that particularly in densely built areas, such as cities, there might not be the space to actually carry out these kind of interventions. A second type of intervention are those on the existing building envelope. So this is particularly the case for, let's say, external walls or masonry infill walls in RC buildings or in steel buildings, where these existing envelopes contribute to the strength and the stiffness of the buildings, but are typically not included in the design. So they can also be the source of severe damage, and not just severe damage to the infills, but also severe damage to the load-carrying elements framing them. And in the worst case, this can even trigger global collapse or pancake failures, as we can see here from an example in L'Aquila. At the same time, from an energy perspective, the existing walls of external walls of a building are the ones that actually cause the highest energy losses through thermal transmittance and air infiltration in buildings. So there's another deficiency in these external walls that needs to be tackled. So some solutions that have been proposed for, let's say, strengthening and improving the thermal insulation of external walls include the application of composite materials such as textile reinforced mortars combined with thermal insulation, the use of prefabricated panels, which can be either CLT panels or timber-based panels, or precast mortar panels that have, let's say, an integration of the structural and the energy perspective. I will give a bit more details on some of these at the end when I talk about the experimental work. And another maybe solution that can be combined with any of these other ones is the replacement of the windows that are often also causing a lot of the thermal heat losses in a building, and combining this with, let's say, structural steel frames around the windows, which can improve the stiffness, particularly for masonry buildings. Some example of CLT panel applications are shown here, and they really show also that such a retrofit scheme, particularly for infilled reinforced concrete buildings, can provide an aesthetic or an architectural upgrade as well as a seismic and energy upgrade. So when we look at the pros of this kind of type of application, is that it's really applicable to any kind of building and can be tuned. So depending on the specific technology that you use, you can apply it to RC buildings, to masonry buildings, and even to steel buildings. Again, depending on the type of application, the invasiveness is much lower than in the case of the exoskeleton application. The need for resident relocation is not always there. So if the intervention can be entirely carried out from the outside, this is a big if, but if it can be carried out, then the business downtime can also be kept low. And finally, if prefabricated or modular elements, so for instance, the prefabricated mortar panels or CLT panels are used, then the application can be relatively fast. On the flip side, let's say, I showed you some examples where maybe the architectural upgrading is desired, but again, if we look at cultural heritage buildings, depending on the type of application, maybe the change of the building facade cannot be accepted, and there's a problem that any of these interventions on the existing envelope, of course, will modify as well the facade typically. On the other hand, by strengthening the infill walls, you will also have higher shear forces acting on the frame members, but also on the foundations. So you always need to evaluate as well the existing frame and the existing foundations of the building, which may also be needed to be retrofitted afterwards. So this can obviously increase the costs and the duration of these interventions. And coming back to if the intervention can be carried out from the outside, the problem is that in many of these applications, for example, for the textile reinforced mortars, a double-sided application is actually much more efficient, even though also single-sided applications can be possible in some cases. And finally, if the substrate of the existing building walls is in too low quality or is already damaged, then such interventions may not be efficient enough. So if we get to such cases where strengthening interventions are not feasible in practice or not economically viable, maybe because the substrate is a too poor quality or has been damaged already, then the replacement of the envelopes could become economically viable, even though it is obviously a much more invasive type of interventions. And here we found two different types of interventions: the ones that propose to use new infills that have better thermal transmittance values, but also are stronger and stiffer than the existing masonry infills. And like this, they can increase the stiffness and strength of the building, but also improve the thermal efficiency of the building. Other solutions are the ones that try to, instead of strengthen and stiffen the building, just increase the deformability of the frame, so reduce basically the interaction between the infill and the frame. And some examples of these might include sliding or deformable joints or gaps between the infill and the frame. Here then, the use of thermal insulation, such as was the case for the, let's say, envelope strengthening and improvement, can also be applied, but also maybe bricks with better thermal capacity can be used, or bricks that are themselves filled with some thermal insulation material could also be used. So when you replace the envelope, you can really achieve any kind of energy efficiency that you would like to achieve. These kind of replacement strategies are obviously only applicable to infilled RC and steel buildings, but not to load-bearing masonry buildings where the walls are actually irreplaceable, let's say. High improvements in energy and seismic performance can be achieved because you can really build whatever new external walls you want. And typically the cost of the materials is relatively low, but then the intervention, of course, with the whole demolition and the substantial amount of waste that is being generated, and the need for relocating the residents also means that the cost of the actual intervention might be higher than the previously described ones. Finally, there's also interventions that are just carried out on the roofs or the floors, on the horizontal diaphragms of the buildings. this would typically be combined with any kind of envelope interventions that we have shown before. So let's say combining an intervention on the walls, but also on the roofs and floors. Here some examples are shown where the existing roofs can be strengthened or stiffened with steel or FRP, for example, and at the same time, thermal insulation and ventilation can be applied in the new roof structure. In masonry structures in particular, this can lead to, so let's say, having a better horizontal diaphragm can improve the seismic behavior substantially. And another advantage, of course, is that it can be combined with the other interventions that we mentioned before. The negative aspect is that these interventions are highly invasive, so you always need to relocate the people, especially if you build new floors. People cannot live in the house, so at least 1 or 2 floors at the same time, the residents need to be relocated completely. So ideally, it's combined with another intervention that is already quite invasive as well. I will not go into details of this because I'm running out a bit of time, but we have done an analysis of these different technologies, and in our recently published technical report, you can find a bit more information how we evaluated the improvements in structural energy efficiency, but also the costs, the impact on the environment, the invasiveness and the level of disruption, as well as the level of integration. So are these truly integrated retrofitting schemes, or are they more coupled? So using one structural and one energy efficiency system and combining this. I will now briefly go through some examples of experimental testing on integrated retrofitting solutions where the JRC has participated. So one part is from the iResist Plus project, where this combination of textile reinforced mortar, or TRM, is combined with the application of thermal insulation. And the other one is the SEP Plus project, which is a collaborative project between COSID in Korea and the JRC in ISPRA, where precast panels are being created that at the same time improve the strength of the existing building and improve the energy efficiency of the building by using capillary tube systems. So first, talking about the iResist Plus combined retrofit scheme. This is basically a combination of these textile reinforced mortars and the thermal insulation. By applying both at the same time, you can achieve higher safety of the building, but also higher energy efficiency of the building, and drive down labor time and costs, because you can really apply both at the same time of application. Currently, this system is being experimentally validated on a typical pre-1970, so non-seismically designed infield RC building. It's being tested under pseudodynamic loading as a 5-story structure. So here you can only see the 2-story physical structure, but there's also 3 further structures that are numerically modeled. And this is being carried out at our lab at the JRC in ISPRA. What is very interesting is that the testing for the first time is a combined seismic and energy testing, where, for instance, for the control building, we start with a blower door test in order to understand if there's any air infiltrations due to cracks or due to, let's say, poor quality of the masonry infills. And then we test the building to increasing levels of seismic damage and reevaluate the thermal capacity of the building due to air infiltrations at each step of the seismic damage. So results of this will soon be published, next steps are now, which is currently carrying out the retrofitting of the building. So as I said, the textile reinforced mortar here shown in blue is combined with these yellow thermal insulation panels. Then other layer of textile reinforced mortar can be applied on top, and like this, next to the structural upgrading due to the thermal textile reinforced mortar, also an energy upgrading of the building can be achieved. And the other system that I would like to talk about is this textile capillary tube system, which is also basically using a similar system to TRM, which is embedding carbon textiles into an adhesive, into a mortar, but as a precast panel. And at the same time, capillary tubes are being embedded into these boards. So the capillary tubes have water running through them, which can be cold water or hot water in order to generate heat or cooling onto the existing wall. So like this, the thermal efficiency of the building can be improved, while at the same time the strength can be improved. And here we have already published the first work on some infilled frames, where we actually compared the TRM plus thermal insulation system tested in the IRISIS Plus project to these TCP panels. And as you can see here on the right, particularly actually the behavior of the TRM retrofitted and of the TCP retrofitted buildings in terms of the seismic behavior is very similar, which is good. So let's say these two systems could be used interchangeably depending on the actual need of the project. So the advantage of the TCP panels, of course, being precast might be the fast and easier application, while the TRM application is a bit more flexible. So you don't need to know already the dimensions. You can apply it, let's say, on site according to the dimensions needed. But in both cases, very substantial improvements in the, let's say, structural capacity of the frame can be achieved, while at the same time, the energy efficiency of the building can also be substantially improved. So to quickly conclude now, my part of the presentation, as I've shown you, there's really a need for seismic and energy retrofitting in many parts of the EU, and this affects a large part of the EU building stock due to its old age. We've identified four main types of integrated or combined retrofitting solutions, which range from exoskeletons to interventions on the existing envelope, the replacement of the existing envelope, but also interventions on the horizontal diaphragm elements of buildings. While many of these, let's say, technologies are still in a very conceptual stage, there's definitely a need to validate experimentally and apply to case study buildings many of these more. And some of these approaches are currently being evaluated experimentally with participation of the JRC. And yeah, I will now go to just quickly present you some of the recent publications from our group at the JRC, and would like to use this as well as an opportunity to thank my co-authors with whom I have worked on this topic for many years right now. So the two, let's say, yellow technical reports are related to the pilot project. Then there's a technical report on the IRISIS Plus project as well as some scientific publications. So if you are interested in finding out more about these activities, please have a look at our publications. And maybe later for the recording can also be useful for people that are interested to look at the references that I've been talking about today. But with this, I would like to thank you and pass the floor back to Marco and then to Kostas as well to deliver the second part of our presentation. Thank you very much.
Thank you, Daniel, for your great and comprehensive presentation. So I just want to remind all participants that the Q&A session will take place at the end of the final presentation, but feel free to post your questions on the chat at any time. Our next presenter is Konstantinos Gkatzogias, who is a scientific project officer at the European Commission's Joint Research Center. His current research work focuses on the regional impact assessment of building renovation scenarios, considering seismic risk, energy performance, and socioeconomic indicators, as well as the development of a rating system for the new European Bauhaus, addressing, among others, sustainability, functionality, emerging technologies, and inclusiveness of buildings and living spaces. He has worked extensively in the development of performance-based seismic design methods for bridges, using advanced nonlinear analysis and statistical processes to inform decision-making among alternative design schemes, including structural control. He has also delivered design projects for the restoration of cultural heritage at the Hellenic Ministry of Culture, and is an active member of various engineering societies and committees. Actually, he was a committee member of within our young members subcommittee, so he has a past experience also in SECET. He holds a PhD and an MSc in earthquake structural engineering and civil engineering diploma. So please, Konstantinos, the floor is yours.
Thank you, Marco, for your kind introduction. I will reshare my presentation.
Yes, please.
Can you see it?
Yep.
Great. Thank you very much again for your kind invitation and introduction. It's good to be back in a way. I will start my presentation following the topics that Daniel presented to you. I will present a framework for regional prioritization that was developed within JRC and specifically within the pilot project that Daniel described a bit earlier. This framework considers for prioritization at the same time seismic risk.
Kostas, I think you just muted yourself. So if you could unmute.
You're still muted, Kostas.
Yeah. Something might have been activated. Yeah, now you're back, I think.
Okay, I didn't touch anything, so I don't know what is happening, but okay,
That's okay, that's okay.
let me try again.
Yeah, I think now you should share again your screen. Yeah. Okay, great.
Okay.
Thank you.
This framework considers at the same time seismic risk, energy performance, and socioeconomic vulnerability. And we will also discuss a bit briefly its extension to evaluate also the impact of renovation coming from alternative renovation scenarios. This is the team that has worked in the development of this framework. You can see people from the Joint Research Center, colleagues from our unit, but also external ones, including Ellen Crowley and Hedvig Norle. This is an overview of the framework that we propose. So you can see that there are two major components, one referring to regional assessments of the existing building stock, and the output of this is used subsequently to formulate some indicators and prioritize regions across the EU. We have practically three assessment routes, one referring to seismic risk assessment, the second to energy performance assessment, and the final one quantifying socioeconomic vulnerability. We use a joint exposure model that I will describe a bit later. And what I will try to do in the next slides is to give you a brief overview of data and models that we adopt in regional assessments, but I will try to focus a bit more on priority regions and our results. So we adopt the European Seismic Hazard Model 2020 for the case of seismic hazard, and we adopt the HDD, the heating degree days, which is a parameter that relies on measurements of outside air temperature. The HDD practically is used to estimate space heating energy requirements in buildings. What you see on the map is practically an average HDD over a decade of data that come from Eurostat. As a reference point, we use the exposure model of the European Seismic Risk Model 2020. However, we extended this to include also energy attributes of the buildings. Practically, we assigned thermal transmittance values in its country, in the buildings of its country, as a function of the construction date. So what we practically did is to subdivide each building class of the European seismic risk model to additional building classes so that we can assign unique thermal transmittance values. The exposure subsequently in terms of population and buildings was distributed from the classes of the European seismic risk model to the extended classes by using some ratios of dwellings per construction date to total dwellings per region, again obtained from Eurostat. Here you can see two snapshots of attributes of the extended exposure model. On the left, you see percentage of buildings built with no seismic design consideration and with low seismic design considerations. On the right part, you see buildings built with a thermal transmittance value higher than 1.6. This value actually refers to buildings from different eras across Europe because practically different values were enforced across Europe during different times. So this value corresponds, for example, to buildings from the 80s in Greece, from the 60s or 70s in France, and even from the 40s in northern countries that traditionally enforced stricter limitations, stricter requirements because of the climatic conditions. These two maps also give us a qualitative indication of the vulnerability of buildings. But of course, we have to integrate this with environmental conditions, seismic hazard and climatic conditions, and the exposure in order to calculate risk and energy performance of buildings. So seismic risk comes from the European Seismic Risk Model 2020. Here, in our case, it is mapped, of course, in the extended building classes that I have described before. And it is also mapped to NUTS 2021 classification system. NUTS is a georeference system which describes the administrative divisions in the countries of the EU. So from seismic risk, we estimate average annual economic loss due to seismic repair, direct loss, and average annual loss of life. In the case of energy performance, we employed an artificial neural network for the sake of reducing complexity because of the many different typologies of buildings across Europe, and of course the resolution of the climatic conditions that I have shown before. So this model uses practically as an input some key energy attributes of the building classes. These are the height of the buildings and thermal transmittance values for external walls and roofs, along with the climatic conditions to ultimately calculate average annual energy consumption, and this can be translated to average annual economic loss due to space heating energy consumption using energy prices adjusted to the year 2020. In the case of socioeconomic vulnerability, we employed composite indicators. Composite indicator is an approach that is useful to describe a concept or idea that it's not very easy to quantify or to measure by using measurable sub-indicators. Here we used the EU Human Development Index, the EU 2020 Index, and the EU Social Progress Index to measure socioeconomic development, inclusive growth, and social progress, respectively. These metrics measure well-being, therefore we adapted them and we combined them in a single measure to quantify socioeconomic vulnerability. In the plots, you see this index, this SVI, plotted from the highest to the lowest value across the EU, and also plotted against GDP per capita. You see, interestingly, that as the wealth increases, socioeconomic vulnerability reduces up to a point. So the relationship is not entirely linear there. So from regional assessments, we evaluate the metrics that I have described before, and we combine them Either we use them in absolute or normalized form, and we combine them to formulate integrated indicators. We formulate single sector integrated indicators. This means that we address aspects only from a single sector. This could be, for example, loss of life and economic loss due to earthquake damage. Alternatively, we formulate multi-sector integrated indicators that practically combine aspects from all three sectors, both from seismic, energy, and socioeconomic ones. In integrated indicators, we normalize the sum indicators and we give the same weight. This was a decision made mainly to reduce complexity, but also to filter out the severe disparities among different sectors. For example, if one tries to add economic loss due to seismic repair with economic loss due to energy consumption and rank regions according to this number, then this will be very close, as in the case that we rank regions only with energy performance. And this is because the associated loss is typically much higher than the loss associated with seismic repair. The most perhaps significant note here is that it is very difficult to obtain a unique prioritization of regions. From our point of view, one should aim for integrated indicators that highlight regions where renovation can have the most widespread impact among different sectors. And of course, considering the scope of the renovation strategy. Let me give you some examples in the case of seismic risk. So what you can most probably cannot see very clearly here are ranked regions in the horizontal axis and three different figures. So in the first one, we rank regions according to average annual economic loss due to seismic repair. This is absolute loss. And this number depends, of course, on the seismicity, depends on the vulnerability, but it depends a lot on the size and the value of the building stock, because it is an aggregated indicator describing a whole region. So on the top, we have Italian big cities and urban regions like Rome, Naples, Bologna, and so on. So if we try now to normalize this with a number of buildings, we get an indicator that highlights again absolute loss per building this time, and urban areas with a high share of mid and high-rise buildings. But again, this indicator depends on the value of the building stock. And wherever the wealth is concentrated, the loss is also concentrated. And in this way, we kind of underestimate a bit the impact of seismic risk in regions of higher vulnerability. And now I'm referring to socioeconomic vulnerability. So if we normalize the absolute loss with the value of the building stock, then we get a more robust indicator to compare regions with different sizes and values of the building stock. As you can see in the last figure, we have on top mainly Romanian, Greek regions that come on top of the Italian ones that we had before in the previous measures. One similar example from energy performance assessments. So in all the maps here, you see average annual energy consumption. On the map in the left, we have absolute consumption. So what we highlight here, we highlight big cities, urban areas, the regions that consume and pay the most. If we normalize this with a number of buildings within the regional building stocks, then we highlight regions with increased consumption per building, severely affected by the climatic conditions. You see an evident shift of prioritization towards the north. If we normalize this also with the climatic conditions to eliminate this effect, then we end up with an indicator that practically prioritizes and highlights regions with building stocks that have inefficient building envelopes and high potential of benefit from energy renovations. In the last slide describing a bit prioritization schemes, I wanted to show to you the differences between different sector prioritizations. So we have on the left priority based on seismic risk. This is practically the indicator of economic loss normalized to the value of the building stock. The same we have for energy performance in green. In blue is socioeconomic vulnerability. And in the last map on the right, we have an indicator that integrates all the previous trends that I have described so far. In red, in this map, are regions, the top 100 regions, considering at the same time economic loss due to seismic repair, due to energy consumption, the energy consumption itself, and socioeconomic vulnerability. These 100 regions practically integrate 10% of the energy consumption and cost, 60% of fatalities, and 50% of repair cost from the total losses across the whole Europe. Moving a bit forward to extending this framework for impact assessment of renovation. With the two boxes on top, now collapsed, you see the previous framework that I have described to you. From this, we get some priority regions that we want to implement renovation. Then we have to set up some renovation scenarios, rerun our regional assessments, but this time considering the renovated building stock and what buildings are we going to renovate. This is defined according to our renovation scenarios. And then we assess their impact, the impact of renovation scenarios with cost-benefit analysis and other impact metrics that I will describe in a while. Here you can see some examples of renovation scenarios that we have investigated. So starting from the first one, a quite simple one, according to scenario one, we promote for renovation some macro taxonomy classes. These macro taxonomy classes are predefined classes based mainly on engineering judgment. For example, this could be, a scenario could be that we renovate all buildings with no seismic design considerations in a specific region. We use the same buildings to investigate the impact from renovating, from applying seismic renovation, energy renovation separately, and then finally integrated renovation. This logic, this approach is useful because it provides a risk-proofed investment in the case of integrated renovation, but at the same time is not so rational when we apply only energy renovation, because practically we renovate for energy performance buildings that have a high seismic vulnerability and therefore a high risk of losing our investment. The second approach, you can see the mathematical formulation, but I will try to describe it a bit in a simple way. So scenario two promotes for renovation a predefined fraction of the building stock within a region. This is based again in engineering judgment. Here we investigated fractions of 10 and 20%. But also 100%, but this is not a realistic scenario. This was done mainly for comparison purposes. So how we select our buildings? We rank the building classes within a region by BCR, by their benefit to cost ratio, as if only this specific building class is renovated within a region. And then we try to add buildings to renovate until this specific fraction of 10% or 20% is reached. Scenario 3 follows a bit of an inverse approach. So in this case, we seek to find the type of the buildings and the fraction of the building stock that can be renovated in a cost-beneficial way within a region. So that renovation of this fraction always results in a net economic benefit. And by net economic benefit, I mean the difference between losses before and after renovation, also subtracting the cost of renovation. So this scenario has two alternatives. 3.1 promotes for renovation all the building classes having a BCR higher than unity. And in this context, the scenario indicates the benefit for individual building owners to renovate their homes. And scenario 3.2, which renovates all buildings within a region that results in a cumulative BCR approximately equal to unity. So 3.2 practically renovates all the building classes of 3.1, but at the same time, it uses part of the net economic benefit to renovate more buildings. And in this way, it is more suitable, let's say, for the case that both the funds and the benefit are handled by a central funding entity. Here you can see how we estimated BCRs either for a specific building class or for a sum of building classes when we calculate this in a cumulative way. So on the numerator, we have the difference between losses before and after renovation, and in the denominator, we have renovation cost. However, both terms are divided here with the replacement cost. And we do this to implicitly consider the variation of renovation cost by country, by settlement type, whether this is a big city or an urban or rural area, and by material. So we consider renovation cost proportional to the replacement cost. Therefore, the denominator is always constant and calculated based on the reference case. And then the effect of renovation cost by country, settlement type, and material is introduced in the numerator by dividing with the replacement cost. We investigated here also the variability of these constant ratios of renovation to replacement cost, and also the variability in the planning period of our strategies, spanning from 35 years up to the extreme case of 100 years. Here you can see some additional impact metrics that we have used in our analysis. This consists of economic benefit in absolute form and net economic benefit as described earlier. We have also calculated the benefit in terms of reducing fatalities, the benefit in terms of reducing energy consumption, and also the percentage of renovated buildings, the percentage of the value of the building stock that it is renovated, and the affected population. The last three practically describe in a way the scalability of the renovation strategy, let's say, and subsequently its efficiency. We modeled the renovation effect in a rather simple way because of the scale of our analysis. So what we did here was to map existing building classes to upgraded vulnerability function. As an example here, we mapped buildings with no design consideration to a medium seismic design code level as the effect of renovation. Similar CDL and CDM buildings of low and moderate code to high code and so on. A similar approach was also followed in the case of energy performance, where we mapped existing buildings to some target thermal transmittance values for envelopes, including walls and roofs. And these target values were obtained from the concerted action energy performance of buildings directive. Here you can see the implementation of scenario 3 across 1,151 regions, NUTS 3 regions across the EU. What you see is percentage of buildings within each region. Note that regions in white are not regions that do not require renovation, but are regions where renovation according to this scenario cannot be applied in a cost-efficient way. In other words, it does not yield a net economic benefit. So perhaps the most striking statement here is the much more extended application, feasibility of application of energy renovation compared to seismic renovation. In energy, we have more than 900 regions where this type of renovation can be applied. Only 62 for seismic renovation. Interestingly, you see that we have a same order of magnitude of regions in the case of integrated indicators, integrated renovation, excuse me. And as you will see in the following, we have the same order of magnitude of benefit in terms of energy consumption, and practically we save double the lives compared to seismic renovation. In the next slide, I aggregated some numbers for the top 100 priority regions that we selected before with the integrated indicators that I have shown. These priority regions are denoted here in red borders. So in this table, where we applied scenarios 3.1 and 3.2, for these 100 priority regions that integrate approximately 11 million of buildings and a population of 31 million of people. So in scenario 3.1, you see that integrated renovation yields the same, actually higher net economic benefit compared to energy performance renovation. We save more lives, almost double of them compared to seismic renovation, and we have the same benefit, the same order of magnitude of benefit for energy consumption. Scenario 3.2 practically uses part of the net economic benefit of scenario 3.1, approximately 200 million, to renovate more buildings, and therefore we increase the benefit. We increase the benefit in terms of reducing fatalities. We have the same order of magnitude again of energy consumption compared to energy, and we increase the scalability of our renovation scenario. In this last slide regarding renovation, a question: what we do with regions where this scenario cannot be applied? What do we do in regions where we don't have a net economic benefit? So this framework can be used to investigate also the efficiency of renovation strategies, of renovation policies, schemes, and incentives. So what you see here is on the left, the map that we saw before, integrated renovation, and percentage of buildings that can be renovated cost beneficially within its region. On the right, you see the same under a hypothetical renovation scheme where 50% of the renovation cost is funded by a central funding entity within a renovation program. You see that we increase a lot the regions where we can apply integrated renovation, and we also increase by far the percentages of buildings that can be renovated. In all the priority regions. I have some conclusions here that I will not go through because I feel like that I'm running a bit out of time. We have discussed more or less all of them. More details, more data, more prioritization schemes and renovation scenarios can be found in our recently released technical and science for policy reports. You can download them from our web platform. There you can also find reports that are not relevant to what I have presented to you today, but are relevant with other activities and actions of the pilot project. Some acknowledgement regarding the pilot project. The project was financed by the European Union, and it was led by our project leader, Silvia Dimova. I have also here some list of indicative references, and with that, I would like to thank you very much for your kind attention.
And thank you, Konstantinos, for your presentation with very stimulating research projects and also case studies. Let's now move to the Q&A session. So I invite all the participants to either write their questions in the chat or even unmute themselves and ask directly our speakers your question. Yeah. Please, Damien, if you want to come off mute.
Thank you. Got quite a few questions, but I'll just start with one for Daniel on heritage structures. You kind of mentioned a lot of the approaches don't really work for heritage because of the sort of invasiveness, particularly the external ones, of course. But you also mentioned on the exoskeleton approach that it was reversible, and that's, you know, a real tenet of heritage upgrade is to have reversible solutions, so that if later on we had a better solution for it, we could come along and demount the retrofit. So I was just sort of wondering, I thought you were going to say that was a good one for heritage, and then you said it was bad, and then all the other ones you said were bad too, except for the less invasive one at the number 4. So just wondering what sort of solutions are out there on heritage.
Yeah, thanks, Damon, for your interesting and tough question indeed. I mean, there's definitely a need for looking at further specifically integrated retrofitting schemes for heritage structures. The truth is that yeah, the advantage of exoskeletons is that they could be removed later down the line, but then if you want to preserve the appearance and you have a shell around it or a structure around it, it's not really applicable. So it also depends a lot on what is meant by the specific heritage structure. So if it's really a cultural heritage building where the facade needs to be protected, maybe some of the interventions on the existing envelope, so for example, the TRM proposals that were investigated in IRISIS Plus, could be applied, for instance, only from the inside of the building rather than from the outside, which is less efficient, but it's a possibility in such cases. Then again, it depends a lot on the type of structure, but if it's possible to change the floors or to change the roofs or to improve the floors or roofs, then these kind of interventions could be applicable. The 4th category, let's say the one on the horizontal members. But yeah, it depends a lot always on the types of materials used, on the types of structures, and what is really the protected part of it. But if you look at our technical report, we have also added a small chapter about heritage structures in particular and some considerations for cultural heritage buildings that today I didn't have much time to get into it, but you can find a few, let's say, works that have dealt with specifically heritage buildings there. And indeed, they include all applications on the insides of walls or on the inside of roofs.
Fantastic. Yeah, great answer. Thank you.
Great. Are there more questions from you, Damien, or was?
I'll gather my thoughts and let other people.
Okay, fine. Other people want to ask questions to Konstantinos and Daniel. Otherwise, I may, yeah. Please, Ren, yep. If you want to unmute yourself.
First of all, thank you for the presentations. So I'd like to ask a question. In fact, some retrofitting scheme involves adding materials to structures, and this may affect the building structural behavior and compromises the seismic resistance. How do we see this compromise being introduced into codes and regulations? Because this is going to be a difficult task and will demand some experience, like for engineers and for the one who will be building this retrofitting. How do we imagine the compromise between all of these factors?
Thank you, Ren. Maybe a question for probably both of you. I don't know if who wants to take the question.
So sorry, Ren, just to clarify, I didn't understand the compromise of what exactly are you referring to?
So some scheme involve like adding materials, like you talked about intervene on the roof or on the inside of the building. So I'm not talking about the exoskeleton, I'm talking about the other schemes. So this is involves adding a mass. And when you say adding a mass, we are going to say that the structure may be more vulnerable to earthquake. So this is some kind of compromise between the energy efficiency and the seismic resilience. On the other hand, how can we introduce this into the regulation? Because we're going to apply this like all over Europe, let's say, and we have different hazards in each country. So this is what was discussed also. So there would be like differences, and this is a very complicated technique to apply. It needs experience, it needs a conception, modeling, numerical modeling that are accurate. So it's a difficult, I think, scheme that, what I said, like compromise the seismic behavior of a building. So how do we see this in our regulation or codes? Or
well, okay, for the first part, of course, yeah, this depends always on what kind of materials are being used. So for instance, the textile reinforced mortars or any other composite systems are usually relatively lightweight. Adding, let's say, steel plates or reinforced concrete, additional jacketing or something like that, which hasn't been discussed actually today, would add weight and needs to be considered in the design. But this is typically what is done already when people do seismic retrofit design, maybe in Eurocode 8 Part 3 or something, to consider the new weight of the structure, of course, in the assessment. But yes, it's obviously something that is important to consider, and ideally using lightweight materials is of course better, but it depends always on the situation, on the type of building, on the type of structure. So it's, let's say, a complex multidimensional problem in any case. And for the second part, yes, definitely, let's say, building regulations and codes and standards are very important for the actual, let's say, implementation of retrofit. So I referred now to Eurocode 8 Part 3 for the retrofitting, in which let's say maybe there's not enough detail on novel technologies. There's still some aspects that are lacking in terms of really describing the details of the schemes. But as far as we are aware, there's also new generations of the Eurocodes coming out over the coming years. And on the other hand, very often, let's say, any kind of codes for renovation, the Eurocodes in particular, but also other international codes, are very often written in a way to give a lot of flexibility to the designer in order to implement new and innovative technologies. So to look more at the, let's say, assessment procedures and to see how far you can get with the retrofit, without having, let's say, specific materials in mind or specific equations for the materials in mind. But I will leave Kostas also to add something on this.
Yes, if I may, interestingly, we started putting forward a new project right now. It's a preparatory action that we will try practically to identify the existing knowledge and develop a rating system for projects, including buildings and living spaces, that will try to address at the same time very diverse aspects, starting from sustainability to functionality and safety of buildings up to aesthetics. It's quite ambitious, but our next steps will be actually to try to gather all the existing knowledge in terms of standards, guidelines, to produce this rating system.
Thank you.
Thank you. There is a question from Oksana. Please.
No, and thank you for the very interesting presentations. I was just wondering, like the long-term performance of these techniques and materials, like are there studies in that line, and how do we make sure that these are durable and energy efficient in the long term? Like in not also in terms of performance, but also in terms of safety in the extreme events, like the textile material or the carbon fiber materials. It's more general. It's not just for these techniques, but from the recent earthquake in Turkey, there was a big concern on asbestos being used in the materials, and when there is a collapse, that's a very big health issue. So I'm just wondering, what's your take on this? Thank you.
Yes, I think this question again addresses my part. Well, the, let's say, material durability of any kind of retrofitting materials is of course a very important topic, and there's quite a lot of research being done on, for instance, the textiles and things like this about looking at the durability. This was not now the aspects that we looked at too much, because we looked more at the combination of it. So let's say in the specific fields of the seismic renovation materials or in the specific fields of the energy retrofitting materials, you will find more information about the durability. So I cannot give you, let's say, a general answer, but I fully agree that it's very important to look at these things. And in fact, also now talking about the Turkey earthquake, we're also very interested from our perspective at the JSC to find out more about what happened in Turkey, for example, with renovated buildings, and if there's some concerns, let's say, about material durability of renovated buildings. So it's a very important point. I don't have an answer for you, but I agree that it's a very important point to be raised.
Thank you.
Thank you. Thank you. Are there any questions from the audience? Again, just raise your hand and ask the question, or just drop a message on the chat. If there are no questions, I may have a question for Konstantinos. Oh, sorry, there's Damien, please.
Oh,
Then I
sorry,
will
Mark,
ask my
didn't want
question.
to-
Yeah,
Didn't
sure.
mean to cut you off there, but
Yeah, that's okay. Please.
it should be a quick one anyway for Daniel. On the embodied carbon aspect of the retrofits you mentioned, it didn't get a lot of mention, but I think that was what was intended by impact on environment was one of your criteria, the evaluation. Because obviously, you know, in terms of the trade-off, in terms of life cycle energy versus initial energy consumption, or indeed embodied carbon. Is that what was included in that?
Yes, there's an important aspect, as you mentioned, let's say, to have a full life cycle assessment. What we did at this stage at the moment is only looking at a cradle to create assessment of the materials only. So let's say just more of a comparison of the materials rather than a full assessment. So to really see if the use of certain materials or the quantities in certain applications cause higher, let's say, embodied carbon compared to others. But we didn't do the full, let's say, life cycle assessment, and including the use stage, the construction stage, etc. But we just looked at the embodied carbons of the material specifically.
And then
Again,
the
you can find
demountable.
more in the report. I left out actually the slide this morning when I realized that I have too many slides already, but yeah.
Cool. No, I look forward to reading that. So like the demountable solution gets credit then for being something that can be obviously reused, and
it would get credit, but not in our assessment,
Not in your
because our
framework, okay.
assessment doesn't look at the let's say final use stages, or even either at the use stage or at the end of service stage. So we just look at the constructor stage and only at the materials themselves.
Cool. Okay, thank you.
Yeah, actually, my question was related to embodied carbon assessment. I was wondering if the energy consumption index, let's say, included something about embodied carbon, Konstantinos, or it's more about the energy consumption in terms of the life of the building.
No, it is just energy consumption in terms of final energy use. We used this neural network that I have presented, and we also calibrated this to final energy consumption coming from Eurostat data. It is an indicator of perhaps emissions, or can be used as an indicator of the consumption of emissions, but this was our strategy so far, at least.
Okay, that's great. I don't see more questions on the chat, so, and we actually have reached the end of the seminar. So again, I would like to thank you for thank the audience for joining today and participating also in the Q&A, and I would like to thank again our speakers for their great presentations, and this talk will be also made available on YouTube. So if you missed any part of it, it will be shortly available. And thank you again, and have a great rest of the day.
Thank you, Marco, again for the invitation and for giving us the opportunity to present a bit our work.
Thank you. Thank you.
Have a nice day. Bye-bye.
Thank you,
Thanks.
Marco.
Bye.
Thank you all. Bye.
Thank you.